It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 46, where today we are going to be talking about the $1 million problems, more commonly known as the Millennium Problems. Now, for the viewers on YouTube out there, you might notice I've got new scenery behind me. I'm not at my house, which is usually where I am, and I'm downtown right now, so not that anyone asked or cares, but I'm still saying it, so yeah, here I am.
Okay, so just before we get into the podcast, as always, as we said last week, we did in fact hit 50,000 downloads during the course of this week, so thank you very much. And we also hit 4,000 Spotify followers. Wow. Thank you very much.
That's crazy.
And we are already at 4,160. So, wow. We might hit 5,000 sooner than we think. Mm-hmm. So thank you to everybody. Thank you to everybody for the follows. And
absolutely.
Yeah, also starting this episode right now, we are going to be picking a comment either on YouTube or Instagram or Apple or anything. If you guys do enjoy the podcast, make sure to leave a 5-star review on Apple Podcasts, because it's a very good way to push the podcast through the algorithm to meet or to reach new listeners. So if you do enjoy the podcast, make sure to leave a comment, and we might pick it and read it out, give you a little shout out in the beginning of a podcast.
Also, we also post regular updates and everything that's happening with the podcast on Instagram. So make sure you check it out. And if you comment something cool on there, it is also a potential candidate for a shout out. So yeah, just keep commenting is basically is the moral.
Definitely. Yep. So this week's comment of the week goes to Utkarsh Kohli. Says, "I can't believe how much y'all have progressed. Been here since day one." So thank you so much for that nice comment. We absolutely appreciate you being, a listener from way back when we started, which wasn't that long ago.
That's true. That is true.
How long ago was that? Maybe
started in May.
8 months?
Yeah. Wait, what are we in? We're in January.
Yeah, 8 months. We're end of January.
I still remember one of our very first videos on YouTube. It was just obviously no video. It was just a picture. It was back in those days, And he commented on one of them saying, "I love your podcast," and that was, I think, if I'm not mistaken, one of the very first comments that we had got, ever, as the Math and Physics Podcast. And I think that was a really nice thing. So thank you, Utkarsh, for supporting us and continuing to watch. Yeah. It's getting a lot better.
Definitely let us know, what is your favorite episode up to date? Since you've been listening since the very beginning, which one was your favorite? And we'll get back to you on that.
So many to pick from. Oh my.
There's 46 now to pick from. So other than that, definitely. If you want to shout out,
I think we can get into.
Leave a comment, leave a like, leave a follow. Go follow us on Instagram. Wouldn't it be so weird if you subscribe to us on YouTube right now?
That would. No way. I'm pretty sure he's definitely the OG subscriber. He's definitely.
No, I'm just talking about the just someone listening,
the generic listener. Whoa.
Wouldn't it be so quirky if you just hit that subscribe button right now?
I mean, it's so red, it's so big. Just wow, that sounded weird. But just go click it. Let's just start. Let's just get into it.
Getting into the $1 million problems. No, this is not clickbait. This is actually for real. If you've never heard of the Millennium Prize problems, there are 7 problems. Well, there were 7 problems. Now there's only 6 because one of them has actually been solved. Each of these problems, if you solve them, you get $1 million. So
so easy.
Why not take a look at them, see if maybe you have a little intuition, which I highly doubt there is any intuition that that can be used to solve these problems. I think it's more experience as well as creativity, as well as just a lot of wisdom in the mathematical world.
So these Millennium Problems are not, I mean, even though they're known for, giving out that $1 million, it basically started out in the 2000s. It started out in 2000, May 24th, 2000. And it was started by the Clay Institute, or Clay Math Institute, the CMI. And it's kind of a part of Cambridge University. And they're like, hey, there are these problems from the 20th century that no one has solved yet. So now we are coming into a new millennia. So why don't we bring these problems to our new millennia and call them the Millennium Problems? Hence the name.
It's millennium.
Sorry?
You said millennia. Millennia is plural.
It's a new millennia, but
new millennium.
Isn't millennia the plural of millennium?
Yeah, new millennium. We're coming into a new millennium. Anyway,
millennium.
This is not a grammar podcast.
Yeah,
just continue.
True. Okay. Okay, yeah. Coming into a new millennium, we have the Millennium Problems. And I think the goal of a lot of the people who are trying to solve them isn't really the $1 million, but it's more breaking what we know about math and science, mainly math, even though this is a lot of problems relating to physics and some with computer science. It's all kind of it's all rooted heavily in mathematics, and they all regard proving it. Basically, most of these problems have a similar idea. Most of them have solutions, maybe that we know they exist, but we just don't know how to prove the problem itself. The theory itself is unprovable as of today. So we're just going to be talking about, I guess, the different problems and I guess what you could do to get that $1 million, because that's a possibility.
And by the way, just to tell you guys that are listening right now, we actually recorded this introduction to the podcast. This 10-minute introduction.
It's my fault.
Rayhan's computer just glitched out and it just deleted the audio file. So,
yes, I'm
so
sorry.
If you want, let us know. Let's actually post that introduction on our Instagram. We'll post it as kind of like a blooper. And if you guys want to see that introduction, you can head on over to our Instagram and see that.
Okay,
so, anyways,
sure. I mean, we can do that. That would be fun.
Yeah. So to introduce the problems here, I'll start with the first one, which is the one that's already been solved. Okay. And it's the one of them that I'm going to cover today. And by the way, we're not going to talk about all of them because there's a lot of stuff to go over. And, we are limiting the podcast to around 1 hour just to keep it nice and, concise.
To be honest.
But we can, of course, come back.
Exactly. I was just going to say, we might have a part 2, depending on how, if you guys, like this, if you guys want us to continue into the problems, it would be great. But for this podcast, I think we've kind of carefully selected which problems we want to talk about because, we can talk about them. To be honest, though, before we actually do get into it, big disclaimer, big disclaimer, we are not versed in any of these topics whatsoever.
Absolutely.
These are very, very complicated topics in math and science that we have no, what's the word for it? We don't have enough standing to actually talk about it. But because obviously, we've read enough about it, I guess we can just have a discussion, which is what we're going to do. But there's nothing that we are going to tell you that you should hold up to us, don't quote us or anything like that. Because I'm just scared, some of these problems are really complicated to understand. So imagine how complicated it is to explain, because if you don't even understand it, how are you going to explain it? So we are trying to kind of understand it and kind of explain it, so it's kind of like a mix between the two. So we have to kind of find that middle ground. And yeah, big disclaimer.
So yeah, so the first one I'm going to talk about is the Poincaré conjecture. Ooh. And so this was solved by Grigory Perelman, and this conjecture is about it's like a topological kind of situation here, and I'm gonna tell you guys the what's it called, the statement of the
Let's hear it.
of the problem here. So every simply connected closed 3 manifold is homeomorphic to the 3 sphere. Okay.
Wow.
So
Wow,
there are a lot of words in there.
Wow.
There are a lot of words in that claim,
Wow.
and each one of them plays a key role into like what it's actually saying.
Mhm.
And this is a very good example of how mathematics and English is very hard, or not just English, but mathematics and language is very hard to blend together, because some words that are put into language, intuitively don't really translate to what it means mathematically. And so you have these words like simply connected that, it sounds pretty simple. You think, it's simply connected.
Simply connected.
But it has a rigorous mathematical definition that says this is simply connected and that is not, right?
Mm-hmm.
And I'm going to actually talk about this problem in a little bit, but it's about topological spaces and like
we're
objects
actually going to
in those spaces.
we're actually going to be getting into the problems on a little deeper level in a bit, but I think before we do that, as we were talking, we're just going to kind of talk about all 7, just brief description of all 7, and then we go into like a deeper discussion on the ones we chose, so talking about another millennium problem, the one now we're coming to the ones that haven't been solved, the Yang-Mills equation. So the Yang-Mills equation, or the Yang-Mills mass gap equation, is a theory that is used in quantum mechanics. And this is where, kind of in the beginning where I said, how a lot of these problems, they have solutions because we are currently using these problems. It's simply that we don't know how to solve or prove that these problems are true. And again, that statement might not have made much sense, but I'll explain it. So there's a theory known as the Yang-Mills theory, and that basically describes a certain property, a certain aspect in quantum mechanics. And that theory kind of relates how all these particles and all these forces are working together. The idea now is that we already know that this works because we've seen experimental proof, we've used it, and we currently use this theory whenever we talk about quantum chromodynamics. And that's what I'm going to be getting into when I go into the deeper field. So the idea is we can use this theory in this field of quantum mechanics, but we don't know the mathematical proof behind it. Like, why does it work? We don't know that. So that's the whole thing that we're trying to figure out. The mass gap situation, it's called the Yang-Mills mass gap problem, or basically somewhere along those lines. And without getting too deep into it, the idea is to find a lower bound to mass. That's the whole thing. Is there a lower bound to the mass of a certain particle? Because we know that there are some particles that are massless, right? For example, we have the photon. We have this particle called the gluon that is also hypothetically, and it is massless. So the question is, well, if there are these particles that are massless, is there a lower bound to mass? And I'm going to be getting, again, deeper into it when we talk about it, but that's basically the idea of Yang-Mills and mass gap. So yeah.
Awesome. So next up, we have the Riemann hypothesis.
Ooh, the classic.
And so, once again, I'm not going to repeat it. This is a hard question, okay? or a hard problem here. And the Riemann hypothesis is related to the Riemann zeta function, which is a complex function, right? And basically, the roots of the Riemann zeta function have like negative integer. It has negative integer roots and also imaginary complex roots with a real part that is 1/2. And so, as we explained in our types of numbers episode, when you have a complex number, you have a real part and an imaginary part. And so, as this like as what I just said here, the roots, when the zeta function is equal to 0, we can have solutions that have a complex part, and every single complex solution has a real part that is 1/2. And this is related to the separation of prime numbers, which we should actually talk about prime numbers. Make an episode about prime numbers.
I was just thinking about it, because that's awesome, a really topic. Interesting. Prime numbers themselves, I think, Parker and I were talking about this before we started. Prime numbers are so interesting because they're all throughout the number line, and they're all spread out, without a specific pattern. And I guess like the entire, or one of the major ideas of the Riemann hypothesis is to find a pattern to the prime numbers. And is there a pattern to the prime numbers? That would be amazing. Wow.
Yeah, that would be absolutely amazing, because as some people would know, I guess, like prime numbers are very rare, right? The higher you go on the number line, the easier it is to find like factors, right?
Yeah.
The easier it is to find factors of numbers, and so the higher you go, the more spaced out these numbers are. But up to date, turns out there's actually no pattern to find prime numbers.
That's amazing.
And so to actually find prime numbers, there are like supercomputers out there working extremely hard. They just go I don't actually know how they do it, but I'm guessing they just go number by number.
Just check
they go number
divisible.
by number, and they just check all the factors, and then until they get to a number, and they say, "Oh, it doesn't have any other factors except for 1 and itself." Boom.
I'm pretty sure that is actually how they do it, because I think I know what you're talking about, like these supercomputers that the primary focus is to find prime numbers, and recently, I think this was a Numberphile video where they found some ginormous prime number, like something to the exponent of something huge. And again, that was obviously found by a supercomputer, and that's the largest prime number that we know till date. And again, the interesting thing is that we have these numbers that go into the millions and billions, if not a lot more than that, and we still haven't been able to find a pattern. I think that's crazy, because I don't know, there are a lot of parts of reality, there are a lot of parts of, physics and science that simply make sense. Like, F equals ma, like that makes sense. That works for every single object. I mean, except for the extreme cases. It basically works for everything. It makes sense. And
it's funny that we have to mention that.
Yeah.
like, our theory works every single time, except for when it doesn't. But
there are special cases for sure. There are special cases. But again, the point I was trying to make is that it's so interesting that there are these numbers that exist in reality, that we can count, we can measure, that don't make sense. They just don't make sense. There's no pattern, there's no relationship between them, and everything is kind of just lost. So I think that's a little interesting and weird, but interesting, definitely. More interesting for sure. Yeah. Continuing on, we have the very, very famous P versus NP problem. So this is a very famous problem when it comes to computer science, because it's kind of heavily rooted in computer science, because it bases on algorithms solving certain questions. Here's the question. P and NP, what do they represent? So P is the list of solution. Wait, let me think about this, because it's a little interesting wording that I have to make sure that I get right. Because 1 is if an algorithm can verify a certain solution in a given amount of time, can that algorithm also find a solution to that problem? So the question is, let's say we've been given, I don't know, some differential equation or some equation, let's not get complicated. Some equation. And
it's also can it find a solution to that problem as fast as it can check?
Exactly. That's the whole problem, right? No, but also that is a subset of the problem, but there is also the majority of it where it's like there are some solutions that can be verified but can't be explicitly got from the problem itself. And that's the whole question of P versus NP. So P represents the solutions that can be verified. NP represents the solutions that you explicitly, solve for. So let's say, again, you have this equation and you have a solution x equals 5. You plug it in and it works. So if that works, can you find x equals 5 in the same amount of time that you plugged in x equals 5 and solved the equation? That's the whole P versus NP. And a lot of people are, so basically, the main question is P and NP or P and not NP. So what that means is, are there solutions? And this is what a lot of people think, that there are solutions that can be verified but cannot be solved. And that is the common thought right now. And again, no one's actually solved this problem. And again, very, very heavily related to computer science, because it's all about how algorithms and how fast these algorithms can solve, certain equations. So I think this is definitely a problem worth discussing a lot more on, but unfortunately not included in our top 4 today. So yeah, continuing
Very
on.
interesting. But I do think we should keep this introduction a little bit more brief.
Wow, we are already 20 minutes in? There's no way.
So let's just blow through the remaining ones. So we have the Hodge conjecture, which, okay, I'm going to humble myself real quick and just say it is so hard to explain that the Wikipedia page says, quote, "The problem is difficult to explain using words," right? So, this problem is related to algebraic geometry and algebraic topology, and it is not very connected to any real application that you can relate to. It's very mathematical and very difficult. So I'm just gonna leave it at that.
And next one is Navier-Stokes equations. And this this is one of the topics that I'm kind of dedicated to talk about. So I guess I can give a very small introduction. And we have spoken about this for sure with Tom Rock's Math. If you guys have watched that episode, amazing episode. And his doctoral thesis actually depended, if I'm not mistaken, yes, it definitely did, on the Navier-Stokes equations. Why, you might ask? And what are the Navier-Stokes equations, you might ask? The Navier-Stokes equations are equations that model the motion of fluids. And these equations work for every single fluid you can possibly think of. Ketchup, water, gas, fluorine, anything that you can possibly think of that flows, the Navier-Stokes equations model it. And again, the whole question about, well, if it's simply a model, why is it a millennium problem? Because again, I'm going to be getting into exactly why it's unsolvable. But just a quick snippet. In 2 dimensions, the Navier-Stokes equations has unique solutions that can be found. In 3 dimensions, however, the 3rd dimension blows up to infinity. What that means is there is no solution for the flow, i.e.,
but only in specific cases.
Sorry?
Only in specific
Absolutely,
cases.
yeah. It's in
right.
specific cases.
The way you said it was like every time you add a 3rd dimension, it blows up to
Okay,
infinity.
sorry. No, but what I'm trying to say is if you are trying to find a unique solution for every possible input, you will not be able to do that because it blows up to infinity. What blows up to infinity, you might ask? Well, what the Navier-Stokes equation states in 3 dimensions is at certain locations, and I'm going to get further in depth of what I mean by certain locations. In certain locations, certain intervals, the velocity of a fluid is infinity. Now, obviously, that makes no sense, but that's what the Navier-Stokes equation says. So, again, that's the whole question, that there's obviously some kind of, either the Navier-Stokes equation simply does not work for some cases, or we have to find a way around it. And we are currently finding ways around it, and that's what we can continue on to talk about. So yeah, coming on the very last one.
yeah, just to be super, super brief here, because I do want to actually talk about these problems. Okay?
Yeah, I really do.
So
I really do.
The Birch and Swinnerton-Dyer conjecture, okay? So this conjecture deals with certain types of equations. So more specifically, those defining elliptic curves over the rational numbers, okay? We're not going to be talking about this problem today. But let us know, drop a comment telling us if you want to hear about the problems that we are not actually going to talk about today. And so I think I'll start if...
real quick. Can you move the light from, like, the lights directly on your face, eh?
I don't know if I can fix that.
Oh. I guess.
No, whatever.
I guess it's it. Okay, let's start
so I'm going to start with... Poincaré's conjecture.
The first and only solved millennium problem. Let's get it.
That is correct. So, as I said before, the statement is that every simply connected, closed, 3-manifold is homeomorphic to the 3-sphere.
That is insanely complicated.
So, in 2002, Grigory Perelman, he is a Russian mathematician, posted a solution to this conjecture online. He just put it online, and then everyone was like, "Oh,
wait, he didn't take it to the Clay Math Institute or anything? He just posted it?
Absolutely not.
This guy
he posted the solution online, and everyone was like, "Damn, this is pretty interesting."
That's crazy.
And so, in 2006, he was awarded with a field medal, which is worth $15,000 Canadian. Right?
Wow.
That's the award. And he refused to take the field medal.
Wow.
Right?
Wait,
so he was awarded 15.
He didn't refuse the field medal. He refused the money.
No. He refused the prize.
Wait,
right?
he refused the medal?
It.
He didn't refuse the medal.
Okay, I don't know, but it's like, all I know is that he refused it. Like, he refused the money, and I'm pretty sure the medal. Like,
wow.
Anyways, the point is that's not important.
Right? Okay. Continue.
The important part is that in 2010, he was awarded the Millennium Prize for having solved Poincaré's conjecture.
Wow.
And he refused the
$1
million.
Wow. Wow. He refused the $1 million.
He declined it. The institute was like, "Oh my god, here is $1 million for your absolutely insane contribution to the mathematical world." And he's like, "Nah, I don't want that.
I don't believe this." Wow, that's either the most humble or stupid thing that this guy's ever done.
I mean, I think if I were him, I would have just taken it.
I mean, it depends, right, on how he's living his life. Like, if he's already living like a lavish life, and he just solved Poincaré's conjecture, fantastic for you. But like, if you're living like, an average scientist's life, I think $1 million can really help.
But he could have like accepted it and then donated it.
Yeah, why did he just not accept it?
Instead of just not taking it.
That's interesting.
Anyways,
that's really interesting.
That was the drama I was talking about earlier. In total he was offered $1 million or $1,015,000.
Wow. Oh yeah,
just did not take any of it.
Wow.
Right? So let's get into this problem while being as layman as possible, because explaining it is not very easy. But let's start with the first word, right? They say every simply connected ... So what is simply connected? And we are talking about like topology. We're talking about topology.
Okay.
So you can kind of imagine in your head already, like simply connected has to do with like connecting 2 points, right? And simply connected space is path connected and continuously transformable paths. So path connected just means that any 2 points in your space can be connected with like a continuous curve. So there's no interruptions, right? For example, if you had like two separated disks, those would not be path connected, because if you had 1 point on one disk, 1 point on the other, you wouldn't be able to connect it with a continuous curve that is enclosed within that set.
Mm-hmm.
But anything else, right, that is just one blob is connected, path connected. But what makes simply connected a little bit more strong than path connected is that it requires that every path between 2 points be continuously transformable to any other path, right? So an example of something that is not simply connected is a CD with a hole in the middle, right?
Yeah.
So you have like a disc with a hole in the middle. So if you were to have 2 points on that CD, and you have to go right around the hole one way, and another path would be to go around the hole the other way, right? And as you can tell, you're not able to transform one of those paths into that other path without like skipping over the hole in the middle, and that's not allowed. That would make it like a discontinuous transformation.
Mm-hmm.
And yeah, so that is what simply connected means. Next up, we talk about a closed 3 manifold. Now, little heads up, Rayhan and I have not even touched upon these subjects in school.
No.
So we are very unqualified to talk about this. So this is why we rely on wikipedia.ca or
Unqualified.
.com.org.
That was the word I was looking for in the very beginning when I was trying to say we didn't have the standard. Unqualified. Okay, yeah, continue.
Yeah,
Continue.
unqualified. So as Wikipedia puts it, 3 manifold is a space that looks locally like Euclidean 3-dimensional space. And here's a little example that is very relatable, I think. So imagine that you are standing on the earth. Very relatable, right?
Okay.
As we said in a previous episode, it looks flat, right? It looks like it's Euclidean, for example. And Euclidean has like an actual definition, but just to be relaxed on these definitions, we'll just say it's nice. You know, like parallel lines are parallel. Everything works out perfectly. But as you know, if you take 2 parallel lines on a sphere, they will eventually intersect, which makes no sense because parallel lines are parallel.
Well, it's only across. It's not across the. It's only across one of the axes, though, right? Because across the equator, like parallel to the equator, if you have 2 lines. Yeah, if you have 2 lines,
yeah, but that doesn't count though.
Oh,
we're talking about
Okay.
We're talking about like
like perpendicular.
What I'm trying
to
to say
equator,
here,
kind of going. Okay, like the longitudinal.
Yeah, but that's not
lines.
allowed in this. This is not allowed in this situation. But
okay.
I'm not gonna explain all that.
Let's not go too deep. Okay.
So what I'm trying to say here is that, locally, if you zoom in very close to your position, it looks like those parallel lines will always remain parallel, and it looks like your geometry is totally Euclidean and all that stuff. But when you zoom out, turns out, oh, this is curved geometry that we're working with, and it's not just perfect. And to relate that to 3-dimensional space, you know, our space in or where we are in the universe looks Euclidean, right? It looks like if you were to send two parallel lines straight out into the universe, they would never intersect. So locally, everything looks perfectly fine. But what if you were able to zoom out incredibly far, and you were able to see that, in fact, if you were to go in a straight line for long enough, eventually you would come back to your original position from behind, right? Like it's like a 3-dimensional like hypersphere, right? Like for example, as I talked about the ball, if you were to go straight in one direction, you would eventually come back to your initial position. But if you were to zoom in very, very close, it looks like you're just walking in a single direction, like out into infinity, right? And then coming back to the 3-dimensional universe, you know, what if our universe right now is in this shape that if you were to go straight in one direction, you pull up behind it, you're same, anyways, all that stuff.
So basically that's a 3-manifold is what you're saying?
Yeah, it's
Okay.
a space that looks Euclidean locally.
Oh.
That's what
Okay.
that's what Wikipedia says. And the
That's
example
what
was
Wikipedia says.
was my own. The example was mine, but that's what Wikipedia says. So yeah, the next section was homeomorphic, and I took some notes. These are my own notes here, and it says I said that homeomorphism is a continuous mapping that preserves all topological properties of a given space. Let's just give a quick example and move on before things get a little convoluted.
Mm-hmm.
The classic donut mug example, right? Mathematicians can't tell the difference between a donut and a mug.
Mm-hmm.
You know, the reason is because a donut has a hole in the middle, right? And people may think that a mug has 2 holes because of the handle and the cup, but in fact, the cup section is not a hole. You could continuously morph that coffee cup into the shape of a torus, essentially.
It's a donut.
And so that is that the homeomorphism is that continuous map that can shape that cup into a donut, and it preserves all the topological properties, meaning that it doesn't add or remove any holes, for example.
Mm-hmm.
So yeah, so that's pretty much like all of the sections of the Poincaré conjecture that I wanted to talk about.
Mm-hmm.
Of course, the proof is not very accessible to people like you and I. Like, you can look at it, but I'm saying, like, in terms of understanding, it's not very easy to read.
Mm-hmm.
So yeah, I'll pass it off to you, Ray.
Yeah. So I'm looking at the time, and I think we might have to extend this a little bit extra, because we do really want to talk. I do really want to talk about these problems. And first up, I want to talk about quantum mechanics. So let's talk about the Yang-Mills existence and mass gap. So I already kind of gave the small introduction about the Yang-Mills theory and the idea behind Yang-Mills existence and mass gap. Let's go for it. So there's something very commonly known, or at least, as I said, what's used to describe quantum mechanics as the Yang-Mills theory. Now, this theory is specifically used in a field of quantum mechanics known as quantum chromodynamics. What is quantum chromodynamics, you might ask? So, it sounds weird. Chromo might be like, it doesn't mean something with color. You are correct. So, interestingly enough, I know it doesn't make any sense.
Thanks, Ray.
This actually does it, but I guess this is what they just called it. Scientists, when they I guess not figured out, but when they started to notice that there is this force that binds things smaller than protons together. Now, what I'm talking about are the subatomic fundamental particles known as quarks. So quarks are bounded to other quarks by something known as the strong nuclear force, right? And this is known as the color force. I don't know why, though. Like, where does color come from? I'm not too sure.
No
but
idea.
Anyway, this is where quantum chromodynamics comes in and kind of relates this strong nuclear force to what they call the color force. And the idea of Yang-Mills' theory is to not only predict, but also, it's basically a theory of quantum mechanics that shows you how the strong nuclear force and the weak nuclear force, how all of them interact together with these particles. Now, here's the interesting thing. Now, here's the mass gap part, right? Because a big part of this problem, the Yang-Mills existence and mass gap, is the mass gap part. So there are two major streams of quantum mechanics. There's quantum electrodynamics, and then, as I stated, there's quantum chromodynamics. I don't believe there are others. I'm not entirely sure, but quantum electrodynamics deals with photons. Those we know are massless. quantum electrodynamics also deals primarily with gluons a little bit. And these gluons, I know they're all just foreign words. These gluons are the particles that carry the strong nuclear force. And wow, that's crazy. So the idea behind this theory is forgetting photons and gluons, because those are the massless particles, right? Forgetting those. If we're relating the strong nuclear force, right? The strong nuclear force is in almost every single, subatomic particle, like a proton, a neutron, not an electron, but almost all particles contain the strong nuclear force, right?
Is the strong nuclear force also what keeps protons and neutrons together?
Like in a nucleon?
In the nucleus, yeah.
I think, because see, electrostatic.
I thought that's what the strong force was.
No, primarily the strong. Because see, this is a big. This okay, little sidetrack, but a lot of people think the Higgs boson gives particles mass, right? And that's kind of a common theory. That's actually not very true, because the Higgs boson gives a particle only like 10% of its mass. The rest 90% comes from the energy of the strong nuclear force. So the strong nuclear force has so much energy, remember energy and mass are equivalent, that basically translates into the mass of the particle. So the majority of the mass of any particle comes from the strong nuclear force, right? I'm not entirely sure, because I'm thinking it wouldn't really work with the electrostatic force, right? Because a neutron is neutral. So they wouldn't really attract. I'm assuming it might be with the gluon. We're not, again, big disclaimer here, not too sure about how they're together. But again, strong nuclear force primarily with these quarks inside of these subatomic particles. So
we should get a nuclear physicist.
We really should
on the podcast.
To be honest, next time we have like an interview or like a guest that has any knowledge on this stuff, I think we can definitely go into a very interesting conversation, because this particular problem out of the 7 I think is really interesting, because it's the only one on quantum mechanics, and it's the one that, as I said, it works. We use it. It's just that we don't know why it works. So let me again continue to explain. So the idea is, again, there is a zero level energy state, which is more commonly known as the vacuum, right? There's a zero energy. An idea of this theory, another way to rephrase it instead of that mass gap in a little more complicated way, is that any state of any particle that is non-zero, like a non-vacuum state of any particle or of any system, the energy of that system must be greater than the energy in a vacuum plus some constant. Now you must be like, okay, well that's kind of obvious, because the vacuum state will obviously be less than some higher energy state, right? That's the entire definition of a higher energy state, that it has more energy. The interesting part is that there are a few particles where their energy is not high enough. So even though their first energy level is higher than the vacuum state, their mass, the mass difference between the zero state and the first state, is arbitrarily small. And if this occurs, and this is not finitely measurable, then there is kind of like a problem with this theory. So the mass gap basically states that there is, in fact, a gap in the mass between the zero energy level and the first energy level. So a system in the zero energy level will have less mass than a system in a higher energy level. Obviously, I'm breaking it down to the simplest possible words. It's a lot more complicated than this, but this is kind of like a way to, I guess, kind of understand it in a simple way. Because mass gap doesn't, like, it just sounds like, okay, there's a difference in mass. But that is actually very, very fundamental to quantum mechanics, because there are a lot of particles that have some mass that are traveling, at the speed of light or near the speed of light. And people are wondering, well, is this mass arbitrarily small, or can we measure it? That's the whole question, right? So again, we use this on a daily basis. Well, not Parker and I, but scientists use this on a daily basis in quantum chromodynamics. It's a very popular theory. I think we should probably link all the Wikipedia articles or whatever articles down in the description, because it's
actually,
a very interesting read. It's a very interesting read.
The official description of the problems are on claymath.org, which is the official website for the Clay Maths Institute, where they
Probably
do
the
have
best one.
they have the official description as well as the status of the problems right now, and also related links to each problem, like lectures or explanations or whatever, as well as if you want to try to solve it, they have the rules for solving this. So you can't just write anything on a piece of paper and say this is in fact a solution to the millennium problem. They do have rules, which,
there are certain ways to solve it, and there are certain things that they are in fact looking for, because remember, all of these problems that we're talking about today, like they do not have, like, again, the point isn't the money. I think that's a very important point. The point is breaking what we know about science. Because if we can solve something like the Yang-Mills mass gap problem, it would revolutionize how we think about quantum mechanics. Again, it's not going to change your life. It's not going to change my life. But it will change how science progresses. And I think that is, that's what our podcast is trying to do, right? Progress science.
Yeah, and these problems also don't have definite answers that we're looking for, right? Because we're looking for a proof.
Yeah.
And, it is stated in the rules, but for some of these problems, a proof can just be like some general demonstration of how these statements are true. And there is a very specific rule as to what will be accepted and what will not. But it's not like you don't have to provide I don't know what I'm trying to you don't have to provide an actual solution or whatever. It's not like solving an equation.
No, absolutely not. It's a lot harder. It's a lot harder than that. Yeah, because you're actually proving that the thing even exists. Right, so one might have the question now. You might be wondering, sitting at home watching this podcast, well, how can I solve the Yang-Mills existence and mass gap problem? Well, the solution to this problem will provide us with insights on how subatomic particles form. And that, as I said, revolutionized quantum mechanics. Because understanding why there's this fundamental mass gap between these subatomic particles, between these fundamental particles, will provide us with insights and more descriptions into understanding, again, why these particles have mass and why some of them don't. And that right there will already have provided us, information on how these things are forming. And I think that's a really important thing. I do want to leave this problem with the thing that I started with. The basic idea is to find a lower bound to mass, right? That's one of the main ideas. One of a simple way to put it is to find a lower bound in quantum chromodynamics. Again, so we're not talking about the massless particles. We're trying to find, is there an amount of mass that is not arbitrarily small, that is finitely measurable, that we can say, okay, it's different from the zero energy state. That's basically the idea, right?
Very well explained.
Thank you.
So, do we want to talk about the Navier-Stokes equations?
Oh no, we're already 50 minutes in. Oh no, I was so excited to talk about the Navier-Stokes equations. Okay, so I was actually leaving this for the end, save the best for last kind of situation, and turns out we don't have enough time. I think.
Well, we can still talk about them.
I think we can talk about
them.
I think we
the
can
Navier-Stokes equations, are a set of equations, and they pertain to the motion of fluids. Now let's get really elementary in here.
Okay.
A fluid is anything that flows, aka a gas or a liquid.
Some solids too. take that. Like glaciers, for example, like they have motions of flowing. Like if you see like a glacier falling, it will follow a path. And a very common description of fluids is that it fits its container, right? Like water will kind of fit the level of glass kind of thing, and a gas will fill up its entire container. So the idea is that a solid, much like a glacier, like I guess a glacier, you can think of it as, at the end of the day, it is liquid, but a big part of it, a glacier falling down, you don't really expect it to conform to certain levels in the container, but it does, right? So there are even some certain scenarios. Yeah, continue.
I mean, I think that has more to do with like friction than it being a fluid, right? Because
okay, it's not just a fluid. What I meant to say, it flows. It's not a fluid. Okay. It's not, solids are not.
Okay.
Solids are not fluids.
I respect that.
Yeah.
I respect that.
Okay.
And so, I just want to say that within fluid dynamics, what you and I have seen so far is just like the flux of a fluid. Mm-hmm. And also Bernoulli's
principle.
Law, is that what it's called?
Principle.
Principle.
Mm-hmm.
Right. And I think that's it. Like, that's all we've seen, right?
We haven't really personally done a lot, because the thing with fluids is that it gets extremely complicated to the point where there are things that even these equations can't predict. And I kind of skipping the horse, jumping up here, but an important part about fluids, or especially with air, and this also works with liquids, but you can apparently very obviously tell with air, is turbulence, right? Turbulence is one effect that cannot be predicted. Or at least today, at least till what we know today, it cannot be predicted. And obviously, right, because if you think about it, the entire idea of turbulence is these random particles that are hitting each other and going off in weird ways. Let me give you an example, right? At the corner, at the very edge of a wing, like obviously you probably won't see this from an airplane because you're in the airplane, but if you, like, I don't know, any airplane at the very edge, they have that, what's that thing called? They have that thing, like they have that thing to kind of cut through the wind.
I don't know what the name is.
And you'll be able to see at the very edge, as it's traveling at, 700 kilometers an hour, you'll see at the very edge there's a vortex that's forming. And the reason behind that is because all the air that is coming on top and below is all hitting at that one part, at that one point. And at that point, there is no equation, no model solution that can predict what happens at that point because of turbulence. Turbulence is the entire idea of random motion. And this is actually a big problem with the Navier-Stokes equations. So, I mean, like I guess we're talking about it now, but like turbulence, especially with water too, like if water waves crash together, where will each and every particle go? Well, we don't know. Even if we model each and every particle, there are random motions that sometimes just simply can't be taken into consideration, right? Because we just don't have all that knowledge. So a lot of this, again, Navier-Stokes equation helps, but it doesn't tackle every possible real life scenario, that being turbulence. Mm-hmm. Right.
And for example, one way in which the Navier-Stokes equations do fail is that, let's say you have a corner, right? You have water flowing in one direction, and then it turns on a 90-degree angle. And so you can tell that on the outside of that turn, the water particles are going to be, going one way and then turning.
Yeah.
Right? But the closer you get to the inside corner, the faster you have to travel, right? Because you have to go from one direction to another direction. But it's kind of like circular motion, right? So as you're turning, you have a radius of rotation, and obviously the closer you are to that radius, but you have the same velocity because all the particles are coming along the trajectory in a straight line at the same velocity. But as they start rotating, the ones on the outside have a larger radius for their rotation, so they will be moving slower than the ones closer to the corner. But here's the thing. The particles of water, or the molecules of water that are turning directly on that corner will actually have infinite velocity.
Predicted by the Navier-Stokes equation.
Yeah.
Yeah.
Predicted by the Navier-Stokes equation. Of course, we already know that that's not possible.
Impossible.
Right? we already know that infinite velocity is not possible. Right? You know, every time you form a corner with water flowing on it, you get a black hole forming. I think we would know about that by now. The point is that you can have computer solutions, right? Or like computer approximations to these problems. And it just goes by, I think it's like iterating the simulation or whatever. They can get like an approximate velocity, but according to the math, it should just blow up to infinity and you would get no solution. So that's what has to be solved, you know? Why does this happen? And is there maybe a correction, hypothetical correction that can be brought to actually account for these discrepancies, I guess?
Because I guess there are two ways to answer this question. Either, no, it does not blow up to infinity because of this, and this is what happens instead. Or, yes, it does blow up to infinity, and this equation simply does not work in this case. So those are, I guess, the two options for solving it. And obviously you need a very, very, good description of where and how you came to that inference. But basically, that's it. So the Navier-Stokes equations, again, are equations. But the problem itself is not called the Navier-Stokes equations. The problem itself is called the Navier-Stokes existence and smoothness. Now, you might be wondering, that's a pretty interesting name. What do they really mean? So, the idea behind existence and smoothness is existence. There must exist a unique solution for any inputted value. So, let's say I have these two equations. So, they're actually a list of two equations. The first equation is basically relating how mass is conserved. It kind of relates the velocity of the particle and everything. I don't want to get too deep into the actual equations themselves, but just talking about them. The first equation kind of states how mass is conserved, and the second equation states how momentum is conserved by using Newton's second law. Right? So you might be wondering, well, that obviously is correct, right? Like it makes sense. But again, as Parker stated, like there's some moments, there's some locations where this equation simply does not work. So anyways, existence, there must exist a unique solution to a set of inputted points. So if I input a certain velocity, a certain trajectory, going in a certain way, I should be able to get, certain outputs. And if I change it a little bit, I should not be getting the same output. And the output should be unique to each input. So that's the first argument. It must be a unique it must be a unique solution if we were to find a solution to this problem. And the second one is smoothness. Now, smoothness is very interesting because if, let's say, I have a bunch of parameters, right? I have a bunch of velocities that are going in a certain direction, and I get some certain output. Smoothness basically states if I change one parameter, just infinitesimally, if I just change it a little bit, it should change the output just by a little bit. Problem is, a lot of times this doesn't happen, right? By changing the input parameter just a little bit, it sometimes blows up the output parameter to proportions that don't make any sense. And that right there is another problem, right? So I guess the idea to, again, solve the Navier-Stokes equations would be to show that there is a unique solution for every single possible input. And that unique solution, whatever is outputted, will not change too much if the input is also changed. So it's also smooth. And that's another important part of the equations.
And that's why it's so hard, because of turbulence, right?
Exactly,
As you said earlier.
Exactly. Turbulence, that's where turbulence comes in, right?
And this is a prime example of chaotic behavior, right?
Mhm.
Because as we said, this was during the interview with Paul Kushner on atmospheric physics, and we were talking about chaotic systems, how if you were to change the initial conditions of, let's say, a double pendulum just slightly, and there are beautiful animations of this that you can find on YouTube, where they show, like, let's say 20 different possible paths, where the pendulum starts like at the top, and each path has a slightly differing initial condition from the last one. And then you see how these paths start up very circular, very nice, but, you know, a few seconds go by and then everything goes crazy. Everything goes to chaos. And that's kind of the problem in the Navier-Stokes equations, or the Navier-Stokes existence and smoothness problem, is that you change the initial conditions just a little bit and everything goes crazy. So
you might be wondering then, well, I guess I didn't mention this, but the Navier-Stokes equation is used in almost every single fluid modeling, right? It's used in every single case. If, let's say, we're trying to predict climate change, if we're trying to predict atmospheric changes, if we're predicting hurricanes or anything that contains a fluid will have the Navier-Stokes. That's like kind of step one. The first step is solving or figuring out if the input, if it satisfies the Navier-Stokes equations. So you might be wondering, well, if everything, depends on the Navier-Stokes equations, every fluid, how can we have that we don't even know a solution exists? How can it be that it's unsolved, right? So what people do, and this is kind of interesting that after some research today, I found out, I never knew this, but apparently what people do is instead of taking every single individual particle and every single individual particle's velocity and, direction and momentum and all that stuff, which would basically be impossible to compute all of that data, what, atmospheric modelists, or basically anyone that's modeling a fluid, what they would do is the process of averaging. So what that is basically they would take, let's say, for example, a 2-kilometer radius of the sea. Instead of looking at every particle in that 2-kilometer radius, they simply look at the average velocity of that whole 2-kilometer ball. And then they have, a bunch of, 2-kilometer balls, and then it's a lot easier to solve, because now we've reduced this billion particles system to, let's say, 10 particles, right? Because they're just these balls that we're now trying to average over. So we can use these Navier-Stokes equations on these subsets, or on these supersets, on these averaged on these average sets. And when we use them, they still work. They give us values, our planes are flying, our rockets are working. So it's obviously working. Like, the solutions exist, but only when we kind of cheat the system a little bit, because averaging, again, is not necessarily the correct way to do it. It's simply, hey, we can't do every single particle because that's really hard. So let's just average it out. So that's kind of like the easy way out is kind of a way to say it. The easy way out is what we use it for.
Right, so I do think now is a good time to end the podcast. It's already been over an hour.
I mean, as you can tell, look at the outside. It just it was absolutely bright when we began.
Super dark,
and it's just dark, right? It's nighttime right now. It's crazy.
So I'd like to thank everybody for listening to this episode of the podcast. If you have any questions, you can let us know. Any comments, hit us up on Instagram at math.physics.podcast. Also, check out the TikTok, which is at that exact same at.
We haven't been posting a lot of TikToks this week. Don't worry though. I just want to let if you guys are following our TikToks, and you must be like, where are these guys' TikToks? Don't worry. Just small technical difficulty. We had a recent transition between who's editing our video. It went from me to now we have a video editor. So we're still making sure everything is in place and everything. So don't worry. TikToks are coming soon. They're going to be cool. It's just It's gonna take little bit of time.
All right, so thank you, everybody. Make sure to follow the podcast wherever you're listening to this, and that is it for us. So this has been episode number 46 of the Math and Physics Podcast, and I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.